please welcome the CEO of the Optical Society, Liz Rogan.
Hello and welcome to FiO, the 100th annual meeting of the Optical Society. What a remarkable achievement, yes? It's an honor to serve as OSA's CEO during this very epic occasion. And I wanted to take a moment to recognize two people who have made this possible. Chris Dainty, who is from the University College of London, who's the chair of the planning committee for the Centennial, and staff Monique Rodriguez, who co-planned and executed a year's worth of programming. So last night's bash and this day's program are two examples of their efforts. Please join me in thanking them. So OSA's birthday is an opportunity to reflect on the accomplishments of the Society and its members. In 1916, a small group of people gathered from national labs like NIST, from industry like Eastman Kodak, from universities. And they organized around the theme of photography, optical instruments, optical materials, vision. They understood the importance of this technology, and they also understood the importance of connecting and collaborating. Imagine today if our founding members were sitting in the audience and listening to talks on light-controlled matter or silicon photonics, they would have been thrilled. So, the OSA has also been very fortunate to receive many, many recognitions for its centennial from other organizations, other partners around the globe. Just this week, we heard from the New York Governor Cuomo extending his congratulations, and the US President Obama from the Office of Science and Technology offering their extended congratulations. So our next speaker understands the importance of government and understands the importance of how science and government need to partner together in public policy. All of you work in different countries, live in different countries, no matter whether it's Brazil, Germany, South Africa. Government is critical in science discovery. Louise Slaughter is the longest serving woman representative in the House of Representatives in the US. She is an incredible advocate for not only the optics industry, but for Rochester. She has been an amazing voice for women, for diversity, and for science education. She was an incredibly critical role she played in the formation of AIM Photonics, the American Institute of Manufacturing, by connecting the Department of Defense, the industry, the optics industry, the universities, the National Photonics Initiative, and organizations like OSA. And one thing I didn't know about Louise, that she's the only microbiologist in Congress. Thank God. She's also been instrumental in pushing through a congressional resolution, which is really important, that recognizes OSA's centennial. Please join me in welcoming Louise Slaughter, Congressman Louise Slaughter, to the podium for some brief remarks. Thank you.
Good morning. Welcome to Rochester, everybody. My goodness, look at this wonderful crowd. This is indeed an extraordinary day. As a matter of fact, last night as I was pondering the speech and just really understanding that we would be in the company of 7 Nobel laureates, I asked myself, I wonder what everybody else in the world is doing today. But thank you, Liz, for that warm welcome, and thanks for the strong leadership that you give to OSA. It's exhilarating to be celebrating this remarkable milestone with so many friends and dignitaries, including the 7 Nobel laureates. And also, they're doing extraordinary work. But I am, excuse me, today's advancement got their roots more than a century ago, when a man named Pearlie Nutting, a scientist at the U.S. Bureau of Standards in Washington, moved here to take a position at Eastman Kodak. Pearlie worked with local luminaries to create the Rochester Association for the Advancement of Applied Optics 100 years ago today, and then he formed the Optical Society. So we have a great deal to thank Pearlie Nutting for. Our world has not been the same. The Optical Society has grown dramatically from just 9 scientists in Rochester back in 1916 to more than 19,000 members in more than 100 countries today. This growth mirrors the extraordinary strides made in optics and photonics over the last century, which have impacted every aspect of our lives. The phones that some of you have in your hands, although they are on silence now, we all got that message. Right now, to share this conference, developments on social media are perhaps the most ubiquitous example of this. Just a few years ago, you needed a bulky, heavy equipment to take a good photo. Now some of the best cameras in the world are right in our pockets. I was talking to my staff the other day about the first mobile phone that I had. It plugged into the cigarette lighter in the car, sat on top of a thing that was as big as a shoebox, and had a handset on top of it. And we really thought that we were modern and exactly up to date. So as Liz said, I'm incredibly proud to have led a 3-year effort to bring the Photonics Institute to Rochester. Excuse me, I have the Rochester throat. I hope you'll excuse me that this morning. You understand that. But we showed leaders at the highest level of our government the amazing work that was already being done here in photonics. So we make no mistake, the history that we're making right now here in Rochester in partnership with OSA is being felt around the country and around the world. That was especially true this year when students from the Rochester Institute of Technology utilized cutting-edge laser technology to help detect gravitational waves and to further confirm Albert Einstein's theory of relativity. The University of Rochester is also conducting groundbreaking research every single day at its world-class laser lab and in fields like bioimaging research, while training students for a future in fields like optics and polymer science. Now, we have a number of students with us here today, and I am very proud of them. Along with their Paul Conroy, their advisor, we have about 25 students from a wonderful optics center being at East High School here in Rochester. I've toured it. It's absolutely remarkable what they're doing, and they're going to be the next generation of optics scientists. We also have children here from the North Star Christian School. And that's good because they too get to mingle with 7 Nobel laureates. Revel in that, children. Now, I have no doubt this is just the beginning of what we can do if we will keep making the research money available in this research. But as we know that the 100-year anniversary of this is really just the beginning, I know that we are well positioned for yet another century of discovery that will continue to shape our region, our economy, and redefining our lives. Thank you all so much for being here. Rochester welcomes you wholeheartedly. Thank you very much.
Please welcome OSA President Alan Wilner.
Representative Slaughter, you have been synonymous with critically supporting optics and photonics for decades. It has impacted Rochester, the entire OSA worldwide community, and indeed our entire society. We all deeply thank you. Let's also thank Liz and her wonderful staff for a fantastic week-long celebration. Happy 100th birthday. It's been a wonderful year for the Optical Society. Light the Future program has been a key feature of our Centennial celebrations. The Optical Society has taken on the charge to teach and inform, as well as build a community of scientists, engineers, and business leaders involved in advancing the science of light. A century milestone is an opportunity for reflection on our achievements and anticipation of how science of light can continue to improve society. We created the Light the Future series to toast a century of optics with an eye towards the future, to inspire our colleagues to explore the possibilities of optics and to challenge us to be advocates for science. As Representative Slaughter said, smartphones measuring gravitational waves, amazing, things we did not imagine could be done. It is exciting to imagine what we will be able to do in the coming decades. I want to thank our dedicated volunteers and staff without whom this program would not have been possible, to thank the chairs and committee staff who have planned this quality conference and exhibition, and to our generous Centennial sponsors, Thorlabs, Corning, and many others. I'd like to also thank the Centennial Committee that has spent more than 2 years planning for this occasion and the whole year's Centennial events, along with, of course, our wonderful staff. We have a full program featuring futurist Professor Michio Kaku and 7 Nobel laureates who will help us ignite the future. In a recent TurboTax TV commercial, Professor Kaku was asked to explain what is zero, and he said that it means the absence of something. And I turned to my son during one of the commercials, and I said, I'd like him to explain what is, instead of zero, what is infinity? And my son said, well, then it's everything. And I said, maybe not. And then so you will be treated to a futurist today. Our moderator is Professor Sir Peter Knight. He's an OSA Fellow, 2004 OSA President, and Professor Emeritus at Imperial College, and also a person for whom I have the deepest admiration and affection. Peter is no stranger to the Rochester community. He joined Professor Joe Eberle's group at the University of Rochester as a research associate in 1972, and he has been publishing, teaching, and winning awards for nearly 50 years. And even now, he still has the youthful, intellectual curiosity and excitement in learning new ideas. He is also a member of the Royal Society and was knighted by Queen Elizabeth for his work in optical physics. Peter is also an advocate of optics and science policy, having served as chair of the UK Defence Sciences Advisory Council. Please join me in welcoming to the stage Sir Peter Knight.
Thank you, Alan. I'm really honored to be part of this celebration of this wonderful society. And boy, did we have fun last night. I'm looking at all sorts of baggy eyes out there, not just mine. Today's Light in the Future speaker gives us a perspective into the future of optics, the universe, the brain. You probably read his book, The Future of the Mind, and marveled at our role in making the stuff of last century's science fiction into reality. Many questions are posed and answered. Will robotics join with our neocortex to allow the paralyzed to walk again? Will medical imaging help to eradicate cancer and improve healthcare in developing countries? These are the kinds of things that Michio has addressed in his writings. He's the co-founder of string theory. He grapples with these and many other issues. A theoretical physicist, a best-selling author, renowned futurist, and a popularizer of science, a real polymath. He makes the complexities of science understandable to the general public, whilst continuing his efforts to unite the 4 fundamental forces of nature in a grand unified theory of everything. You may have seen him, of course, on the media. I'm going to pick up the BBC, of course, being given my accent, but also CNN, CBS. Michio has been in pursuit of scientific discovery from a very early age. We've discovered that as a high school student in California, He built a rudimentary atom smasher in his parents' garage. According to a retelling in Wired magazine, it was powerful enough to blow their home's fuse box, I love this next bit, with electromagnetic coils that could pull fillings out of teeth. Not quite the Large Hadron Collider, but incredible for a teenager. Michio was first in his graduating class at Harvard, earned his PhD in 1972 from the University of California at Berkeley, where he worked at the Rad Lab. He was a lecturer at Princeton and spent the majority of his career teaching at CCNY, where he holds the Henry Seamat Chair and professorship in theoretical physics. Now, right at the beginning of this celebration, you were told about the Twitter feed and the hashtag. I'm going to say that there is a thing that's based on Twitter feeds called the Kardashian Index. Professor Kaku is one of the leading figures in the Kardashian Index, one of the scientists right at the top, supplanted to some extent by Kim Kardashian. But what an achievement for a scientist. He's here with us this morning to share his outlook for the universe and the brain. Please welcome me in join me in welcoming to the stage Michio Kaku.
Well, after such a great introduction, I can't wait to hear the speaker myself. First of all, let me say that some of these honors can actually backfire on you. Let me make a confession. Recently, New York Magazine had a contest who are the 100 smartest people in New York. I'm proud to say I made the list. However, in all fairness, I have to admit that Madonna also made that same list. And they tell me that next year Lady Gaga is going to push me off the list entirely. Now today I'm going to do something dangerous, very dangerous. We are here, of course, to celebrate the 100th anniversary of the founding of the Optical Society. I'm going to make a prediction for the next 100 years. Close your eyes and imagine that we're in the year 1916. Everyone's talking about a revolutionary new invention, only 20 years old, called the light bulb. And then someone announces at that meeting that one day we will have light beams that can blast through steel. Light beams that in principle could carry all human written knowledge. Light beams that could be shined on to the moon and detected by astronauts. That we would have probes on Mars and Jupiter and Saturn. You'd be considered absolutely nuts. Well, that's what I'm going to do today. I'm going to try to predict the next 100 years. Of course, it's very dangerous to make these predictions. Let me quote from that great philosopher of the Western world, Yogi Berra. Yogi Berra once said, quote, "Prediction is awfully hard to do, especially if it's about the future." Actually, Niels Bohr said it first. But Yogi Berra also said, on the road to predicting the future, if you encounter a fork in the road, be sure to take it. And even Woody Allen once said, talking about the future, Woody Allen once said, quote, "Eternity is an awful long time, especially toward the end." Well, you know, predictions are easy to make. When we physicists wrote the World Wide Web, the World Wide Web was written at CERN. It was devised to keep track of subatomic particles. That's why we physicists created the World Wide Web. One physicist there made a prediction. He predicted that the World Wide Web would be a forum of high culture, high art, and high society. Well, today, of course, we know that 5% of the internet is pornography. But that's because teenage boys log on to the internet. Just wait until the grandmas and the grandpas log on to the internet. Then 50% of the internet will be pornography. And sometimes people come up to me and say, "Professor, come on, give me a break. You physicists, I mean, what separates you from chemistry or all the other great sciences?" Well, let me tell you a short story about World War II. During World War II, the Nazis captured a group of American scientists. There was a geologist, a physicist, and a chemist. And the Nazis said, "These are spies. They must be executed." So they put the geologist in front of the firing squad. And they asked the geologist, "Do you have any last words?" And the geologist suddenly yelled, "Earthquake! Earthquake!" Well, everyone scrambled for cover, an earthquake. And in the chaos, the geologist snuck out. Well, then they put the physicist in front of the firing squad. And they asked the physicist, "Do you have any last words?" And the physicist yelled out, "Lightning! Lightning!" And everyone scattered, and the physicist snuck out. Then they put the chemist in front of the firing squad, and they asked him, "Do you have any last words?" And the chemist said, "Fire! Fire!" And before I begin to give you a guided tour of the future, let me make a short statement. It was stated that, yes, when I was in high school, I built a particle accelerator, a 2.3 million electron volt Betatron particle accelerator in my mom's garage. She kept wondering to herself, why can't he play basketball? Maybe if I buy him a baseball. And for God's sake, why can't he find a nice Japanese girlfriend? Why does he have to build these particle accelerators in the garage? Well, that got me a scholarship to Harvard, and it began my professional career. So I owe it all to a particle accelerator. But let's begin, because today I would like to talk about the future. Can I go backwards on this thing? Hold on a second. Go back, right. This book here, I actually predict the next 50 to 100 years in artificial intelligence, nanotechnology, and biotechnology. And in this book, I answer the question that has haunted philosophers for generations, that has haunted theologians. And that question is, that I answer in this book, is there intelligent life on the earth? And the answer is obviously no. Have you seen the presidential debates? Obviously no intelligent life on this planet. And then in my other bestseller, I talk about 500 years into the future where you might have time machines, teleportation, starships. And in this book, I address the question, what happens if you enter a time machine, which is allowed by Einstein's equations, by the way, and you meet in the past your teenage mother before you're born, and your teenage mother falls in love with you. Well, if your teenage mother falls in love with you before you're born, you're in deep doo-doo if that happens. But in physics, we have something called the many worlds theory. So that if you meet your teenage mother before you're born, she's not really your mother. She's chemically identical, same DNA, but she exists in a parallel universe. And then my latest book, The Future of the Mind. I talk about how optics will eventually unravel one of the greatest secrets of inner space, and that is consciousness. One day, the internet will be replaced by BrainNet. We will send not just digital signals by laser beams, we'll send emotions, feelings, memories. In fact, the first memories can now be sent over the internet just last year. Imagine uploading memories. Just in case you're a student and you have to upload your calculus exam, wouldn't it be great to simply learn science by uploading memories? I'll talk more about this and how optics is paving the way. But let's say a few things about the frontiers of outer space and inner space. First of all, my first prediction tonight is that either next year or the year after, the people behind LIGO will win the Nobel Prize in Physics. Let's give a hand. They're in this room. I'll say more about that. I'll also talk about the new giant telescopes and the exoplanets that are now being discovered. Imagine doppelgangers of the planet Earth, Earth 2.0. being discovered in outer space because of revolutions in satellite technology and also optics. And I'll also talk about how lasers may one day send the first starship to the nearby stars. Stephen Hawking and billionaires have now backed the Starshot Breakthrough Project, which hopes within 20 years to send the first starship to Proxima Centauri, energized by a laser beam. And then we're going to go into inner space. We're going to talk about the end of Moore's Law. What happens if computers no longer are twice as powerful as the previous year? And also the inner space of the mind. We're going to talk about new developments in what is called supercontinuum science and also optogenetics. One day we will map the entire human brain using lasers. So let's talk about next year's Nobel Prize, and that is the discovery of gravity waves. It was 100 years ago, not only that the Optical Society was created, but this obscure physicist in Berlin writes down and predicts the fact there must be gravity waves. And why? He had a thought experiment, a simple thought experiment. Einstein proposed a relativistic theory of gravity, such that nothing can go faster than the speed of light. Now think about it for a moment. Here's a thought experiment. Children ask this question: what happens if the sun were to disappear right now? Right now, the sun were to disappear. Children ask the question, how long would it take for us to notice that? Think about that. How long would it take for us to notice the fact that the sun just disappeared? Actually, we physicists don't know the answer. But Newton would say instantaneously. Throughout the universe, everybody would know, if they're out there, that the sun had just mysteriously disappeared. Along comes Einstein and says, not so fast, not so fast. If nothing can go faster than the speed of light, then there must be a shock wave that emanates. Outside the shock wave, you don't know the sun disappeared. Inside the shock wave, you know that the sun has disappeared. And he applied this also to electricity and magnetism. Let's say I have a proton. Everybody knows that at rest, the proton's electric field is given by Coulomb's law. Children learn Coulomb's law. Now think about that. If nothing can go faster than the speed of light, and you move that proton, there must be a wave of electricity that emanates from this proton. Inside that sphere of disturbance, inside this sphere, you know the proton has moved. Outside this sphere, you don't know the proton has moved. That shock wave, what is that shock wave that travels at the speed of light? It is magnetism. People ask the question, what is magnetism? Magnetism is a byproduct of relativity, because nothing can go faster than the speed of light, including Coulomb's law and electric vibrations. And then, if you have two such objects chasing each other, like a dog chasing its tail, two pulsars, then the radiation emitted should be measurable on the planet Earth. And that's how gravity waves were first indirectly detected. So let's now compare something you're familiar with: Maxwell's equations and then Einstein's equations. First of all, here is Maxwell's equations written in relativistic form. It simply says that the divergence of an antisymmetric second-rank tensor equals a 4-vector. In fact, it is the simplest equation you can possibly write for a 4-vector. And what does it give you? Bingo! All of electricity and magnetism comes out of that simple equation. And how do you derive it? By simply moving a proton and imposing relativity on that proton. Now let's do the same thing for gravity. Aha! Now for gravity, we don't start with the 4-vector, we start with the second-rank tensor, here shown on the upper right. And then we insert an ansatz. Let's take a guess at what a disturbance would look like in gravity, and you put it in. And what do you get? Bingo! Gravity waves. In 1916, when Einstein wrote down relativity theory just the year before, he realized that gravity waves have to exist. If they don't exist, then the theory is totally wrong. This is the acid test. Now we know for Maxwell's equations, you have to have waves. These waves, caused by relativity, are called magnetism. That is the origin of magnetism. That's why we have magnetism. Magnetism is a byproduct of the fact that nothing can go faster than the speed of light. So let's take a look at the polarizations now. For a 4-vector has two components, giving you two polarizations. That's why we have polarized lenses. That's why we have polarized glasses. But gravity is based on a second-rank symmetric tensor. Therefore, look at the vibrations that you get. They're quite different from the normal vibrations you get using light. But again, the physics is the same. Nothing can go faster than light, not even information. Therefore, gravity waves have to exist in the same way that magnetism has to exist. Without relativity, there is no magnetism. And here is LIGO. It is perhaps one of the crowning achievements of the National Science Foundation. We're talking about two large detectors, one in Washington near Hanford, and the other one near New Orleans. And we have two laser beams that intersect. And if there is a gravity wave from a colliding black hole, it will jiggle the distances slightly because, of course, we're jiggling the fabric of space and time, and it creates an interference pattern that then matches the prediction of Einstein's theory. Remember that back in the 90s, two physicists already proved that if I have two pulsars rotating around each other, they will decay. A very small amount of decay each revolution, and that was measured, and it conformed exactly to Einstein's equation. Again, if you take a look at Einstein's equation and do the same calculation, you get exactly the results found by the LIGO group. So that's today. But today, we're also going to talk about the next 100 years. What will this experiment look like 100 years from now? The next step beyond earthbound gravity wave detectors is to put them into outer space. In outer space, you can have detectors separated by millions of miles. And one of the problems with LIGO and earthbound detectors is vibrations. If a truck goes by near LIGO, you have to compensate for it. The waves of the Pacific Ocean have to be compensated. You have to compensate for all these tiny microscopic vibrations. In outer space, you don't have to worry about that. So look at this chart here. First, we're talking about earthbound detectors on the lower right. Next, we're talking about putting these into outer space. And then we're going to look at pulsars. The pulsars, using pulsars as a very accurate clock. So this is LISA. In the next few decades, we don't know exactly when, it keeps being delayed because of budget cuts. The bureaucrats will finally tell us when we can put LISA into outer space. This is the Laser Interferometry Space Antenna. It is 3 million miles across in one version. A gravity wave from colliding black holes hits this detector, jiggles it slightly because we're jiggling the fabric of space and time. And then we can begin to pick up vibrations, not just from colliding black holes, but we can dream about creating by detecting radiation from the Big Bang. So the next prediction is, with space-based gravity wave detectors and with pulsar timing mechanisms, we'll be able to not just see into black holes, but into the Big Bang itself. The secret of Genesis, the secret of the universe, may one day be revealed by laser beams. You see, we physicists know that there was a bang. We don't know why it banged. We don't know what banged. And we don't know what set off the bang. All we know is that it banged. That we know. Everything else is a total question mark. And we will actually have, with perhaps the next generation after LISA, information before Genesis. What happened before Genesis chapter 1, verse 1? In the beginning. Well, what happened before the beginning? I'm working something called string theory. String theory is a finite theory. It takes you before the Big Bang. And optics. Optics may one day give us a clue because we'll get radiation from the instant of the Big Bang. Right now, you've seen these photographs of the shock wave, the background cosmic radiation. That radiation dates after about 300,000 years after creation. 300,000 years after the Big Bang, we had a period where the universe became transparent before it was opaque. And that light that you see in those photographs dates from that era. With gravity wave detectors, we can go to the instant of the Big Bang. And in string theory, we hope to have baby pictures of the infant universe emerging from the womb. And maybe we'll see an umbilical cord connecting our universe to a parent universe. The leading theory of Einstein says that the universe is a bubble of some sort. We live on the bubble is expanding. That's called the Big Bang theory. String theory says there are other bubbles out there. And perhaps when these other bubbles are out there, they create a bubble bath of quantum universes. When they collide, or when they peel off a baby universe, that is the Big Bang. So the Big Bang, we think, may one day, using laser beams in outer space, be measured to give us understanding of parallel universes. And then the next question everybody asks is Elvis Presley still alive in a parallel universe? Well, can't be ruled out. And now let's talk about the next 100 years of optical telescopes and the search for exoplanets. There have been two developments over the last several decades that have really rejuvenated optical telescopes. First of all, it was 400 years ago that Galileo took the telescope and pointed it to the heavens. And that opened up a universe of discovery. And then during World War II, radio telescope comes into its own, and that allows us to peer into quasars and galaxies and galactic nuclei. That was the second great revolution, radio telescope. The third revolution is gravity wave telescopes, gravity wave detectors that can peer into the heart of a black hole and the instant of creation itself. Two developments of the last 2 decades. One is segmented mirrors that can be moved independently, millisecond by millisecond, and then adaptive optics compensating for the vibrations and the disturbances in the atmosphere due to thermal currents and things like that. The latest pictures from these telescopes rival the quality of pictures from the Hubble Space Telescope. It's not going to replace the Hubble Space Telescope, complements it, but think about that. Telescopes on the planet Earth using adaptive optics and segmented mirrors can begin to rival the quality of pictures from the Hubble Space Telescope. And what are we going to do with this information? Search for Earth 2.0. Right now, we have a handful of exoplanets that look very similar to the planet Earth. One day you will go outside, look in the heavens, and have an existential shock, knowing that somebody out there is looking back at you from outer space. We're talking about the fact that with ground-based telescopes and with the Kepler satellite, we can now create the first census of the Milky Way galaxy. Who would have thought that one day when you look at the Milky Way galaxy, we can actually understand what percent of these stars have planets that are Earth-like. The latest developments are 50 to 100% of the stars you see at night have planets going around them. This is amazing. 50 to 100% of the stars you see at night have planets going around them. And of them, about 1 in 20 of the stars you see at night have Earth-like planets going around them. And so we now have the beginnings of a census in our own backyard. So this means that microbial life could be much more common than we previously thought. 1 billion, perhaps 1 billion Earth-like planets in the habitable zone where we have liquid water oceans. And the next generation of telescopes may give us spectroscopic information of the presence of liquid water and oxygen. Liquid water is perhaps the most precious commodity in the universe. Water is quite common, but liquid water, the amniotic fluid of life, is extremely rare. I mean, in our solar system, where do we find liquid water? On the Earth, and then maybe perhaps in Europa or Enceladus, but that's about it for our solar system. And so we're talking about the ability to zero in on planets that resemble the planet Earth. The next question that everyone asks is, how come they don't land on the White House lawn and announce their existence? Well, if you walk down a country road and you see an anthill, do you go down to the ants and say, I bring you trinkets, I bring you beads, I bring you nuclear energy, I bring you higher mathematics, take me to your ant queen? Or perhaps you have the strange urge, politically incorrect urge, perhaps to step on a few of them. Well, if they're that advanced that they can land on the White House lawn from thousands of light years, we're sort of like ants to them. I mean, we're so arrogant to believe that they will actually want to visit us. Think about that. But look, here are the candidates now for super Earths. They're a little bit bigger than the planet Earth, but they have all the appearances of having liquid oceans. We don't know for sure. We still have to zero in on the spectroscopic information, but the conditions are ripe for them to have liquid water oceans. And so this is going to give us an existential shock, knowing that out there, just in the night sky, almost all the stars you see in the heavens have planets going around them, habitable planets. And then the next question is, can we visit them? It used to be thought that to create a starship would take a technology 100, 200 years more advanced than us. Well, because of optics, we may be able to go to the stars in 20 years. Stephen Hawking, along with a group of billionaires, have announced the Breakthrough Starshot program to use a bank of laser beams with the power of 800 gigawatts to fire at a bunch of parachutes, each parachute containing a chip the size of a postage stamp, and blast them into space so they accelerate up to 20% the speed of light. 20% the speed of light. And they reach Proxima Centauri, the nearest star, in just 20 years. I mean, think about this. Because science fiction always talks about gigantic rockets like the Enterprise or the Millennium Falcon. Nope. The first starships to arrive to Proxima Centauri may be the size of a postage stamp. And how many of them? Thousands of them. Think for a moment about Mother Nature. How does a tree or a plant propagate its seed? Plants give rise to thousands of seeds, almost all of which never survive. But some of them do survive to propagate the next generation of plants. That's how Mother Nature does it. We humans are different. We nurture our young. Plants couldn't care less about their young. They just create lots and lots of seeds, and that's how we should go to Proxima Centauri. We should have laser beams energizing postage stamp chips, chips which are intelligent, chips which have television cameras, which have sensors, radio to communicate back to the planet Earth, and perhaps this is how we will begin the exploration of the universe. At the end of the talk, I will give you an even more elaborate way to go to the stars. So then the next question is, what is the universe made of anyway? Well, every high school textbook says the universe is mainly made out of atoms. Well, that's wrong. In fact, every single high school textbook in science is now being rewritten because the universe is not mainly made of atoms. In fact, we're clueless. We're clueless as to definitively answering the question, what is the universe made of? First of all, dark energy, the energy of nothing, empty space that pushes the galaxies apart, that's giving us the Big Bang Theory. 73% of the matter-energy universe comes from invisible energy that fills up the vacuum. 23% comes from dark matter, matter which is invisible, but yet holds the Milky Way galaxy together. The stars you see at night, the stars you see that night that fill up the galaxy only make up 4% of the universe. And what about you and me? You and me make up 0.04% of the universe, the higher elements. Now, what about theory? The latest theory of dark energy, the most reliable theory, estimates the amount of dark energy in the universe. It's called the cosmological constant. It is off. It is incorrect by a factor of 10 to the 120. that is 1 with 120 zeros after it. It is so big, there's no name for a number that big. It is the biggest embarrassment in all of science. In all of science, we do not see a bigger mismatch between theory and experiment than 10 to the 120, which makes up the energy of the universe, the energy of the expanding universe. In fact, if one of you ever figure out what is dark energy, be sure to tell me first. We'll publish together, of course, share the Nobel Prize. But what about dark matter? Even if dark energy is off by 10 to the 120, we do have optics. And optics gives us a clue about the distribution of dark energy, dark matter. First of all, dark matter is invisible. If I have some dark matter in my hand right now, some dark matter in my hand, first of all, it would sift right through my fingers because it doesn't interact electromagnetically with my fingers. It would dribble through the podium. It would go all the way to the center of the Earth because it has gravity. It would go all the way to China. In China, it would reverse direction, come back, and meet me here in Rochester. That is how bizarre dark matter is. Now, we have maps of dark matter, but I just said dark matter is invisible. So how can you have maps of something invisible? Through optics. Because we know, for example, that there is glass in your lens. But how do you know that you have glass in your lens? Glass is invisible, right? Light goes right through glass. But how do you know that you have glass in your lens? Because light bends. It bends when it goes through glass. In the same way shown here, light bends when it goes through dark matter because of gravitational effects. So we have maps of dark matter. In fact, it surrounds the Milky Way galaxy. But what is dark matter? We don't know. I'll give you the leading theory in a minute, but we don't know what dark matter is. But optics, using Einstein lenses, using the movement of light through dark matter, has given us maps of dark matter. In fact, there's dark matter in this room. In this room, there is dark matter. The Earth is moving in a wind of dark matter. But the dark matter is so rare, so difficult to measure, that we don't know that it's in this room. So, then the next question is, what is dark matter made of? Perhaps optics will tell us. But we have a clue. And that is, in Geneva, we have the Large Hadron Collider. It is much bigger than the one that I built in my mom's garage. It is over 27 miles in circumference, some incredible number. It accelerates protons to 14 trillion electron volts. And what do we get for 10 billion euros? We get the Standard Model. Now, there's one problem with the Standard Model. It is perhaps the most realistic understanding of the fundamental nature of reality. The problem with the Standard Model is, it is the ugliest theory known to science. It's like taking an aardvark, a platypus, and a whale, getting Scotch tape, and Scotch taping them together, and calling the platypus and the whale the finest product of evolution that Mother Nature has given us. Why should the fundamental theory of reality be so ugly? 36 quarks, 3 generations of identical particles, over 19 free parameters that you can adjust almost at will. Well, we have another theory. It is still not universally recognized, and it is string theory. This is what I do for a living. This is my day job. And string theory says that the photon, which is, of course, what we celebrate here today, we're celebrating the photon. The photon has an evil twin. An evil twin, supersymmetry, says that all particles should have a partner. The partner of the photon. It is called the photino. The photino has mass, no charge, and it is stable. And what is dark matter? Dark matter, which is something with no charge, which is stable, and it fits all the characteristics predicted by string theory. So what I'm trying to tell you is something very simple. Optics may one day give us a clue as to whether string theory is correct or not, via the satellite LISA, to be launched into outer space perhaps in the next few decades, and perhaps one day we'll find dark matter. But now that we've talked about outer space, let's talk about inner space, because we're talking about the next 100 years. Let's talk about the next 10 years. In the next 10 years, Moore's law is slowing down. We physicists, we quantum physicists, have been predicting this thing for years. Industry would snicker at us. They don't snicker anymore. It is obvious. Moore's law is now slowing down. Moore's law is something that every teenager knows. A teenager knows that your Christmas presents are almost twice as powerful as last year's Christmas presents. Every teenager knows that. But would teenagers upgrade? Would teenagers buy the next generation of toys knowing that it is not as powerful, twice as powerful as last year's Christmas presents? Look at this chart. It's amazing how powerful and how far we've come with Moore's law. Look at the year 1969. In 1969, we put 2 men on the moon. But ever see these old NASA videotapes? They had 64K processors back in 1969. You realize that your cell phone has more computer power than all of NASA in 1969 when they put 2 men on the moon? In fact, you're not going to put me in one of those rocket ships. You're not going to send me into outer space backed up by one cell phone. It's criminal. It's criminal what NASA was doing in 1969, shooting humans to the moon backed up by less than one cell phone. But look at the future. This curve will begin to slow down. Why? Well, quantum mechanics, among other reasons. We etch silicon wafers using ultraviolet radiation. But now transistors are so tiny, we have to go to X-ray radiation. And X-rays, of course, pack a lot of energy because of Planck's equation, and therefore will destroy the silicon substrate. So we can't use ultraviolet radiation to etch anymore. So a number of stopgap fixes have been proposed for the next few years. Intel says, yes, Moore's law is slowing down. It's admitted that now. Its recourse is three-dimensional chips. But three-dimensional chips generate heat because heat is generated as a function of the cube of the distance, while surface area is cooling, and that goes as the square of the distance. Since the cube of the distance rises faster than the square of the distance, your chip melts. So chips of the future have to be cooled, or else you can fry an egg on your laptop computer. X-ray lithography, we mentioned. The problem with that is X-rays are quite energetic. New kinds of semiconductors, yes, other people have tried other things besides silicon. And also parallel processing. That's what Microsoft would like to do. Microsoft also recognizes that Moore's law is slowing down, but perhaps parallel processing will work. But ultimately, quantum mechanics kills you. Ultimately, the electron tunnels through tiny layers, through wires. Heat will vaporize or melt the transistor. So we need a post-silicon era. Silicon Valley could become a rust belt in the future. What are we going to do about it? Well, one is optical computers. It turns out that you can build optical gates, because that is what a transistor is. It's nothing but a gate. You can build optical transistor components that are molecular sized. DNA computers already exist, built at Princeton and other places. Very hard to program, however. Molecular computers, that's my bet, graphene. Graphene will sustain semiconductor calculations, except the world's record for creating pure graphene is about this much. And how do you machine it? How do you machine graphene? That's not known. Quantum dot computers has been proposed. Quantum computers have often been proposed. But quantum computers have the problem of decoherence. Just like with LIGO, the slightest vibration can upset the coherence of your atoms. IBM has set the world's record for a quantum computer calculation. It is 3 times 5 is 15. Now that doesn't sound like much, but that's the world's record for a quantum computer calculation. But hey, here's a homework assignment. Take 5 atoms, go home tonight, and prove that 3 times 5 is 15 on 5 atoms. Then you realize this is hard. This is real hard. But let's move on, because the next frontier is the brain, the mind itself. many new developments in something called neurophotonics. In fact, right at City College, my colleague, Professor Alfano, has pioneered supercontinuum dynamics, by which laser beams can be transformed into ultra-bright white light. And this has applications to things like neurophotonics. Now, neurophotonics sounds like a contradiction in terms. Another contradiction in terms from Silicon Valley is smart Barbie dolls. That's another contradiction in terms. Another contradiction in terms is Microsoft Works. That is also a contradiction in terms. But let's now talk about it. Neurophotonics, the application of supercontinuum dynamics and laser beams into something that has given us maps of the human brain. President Barack Obama announced that the Connectome Project and mapping the human brain is now one of our major priorities. $1 billion was pumped into the Connectome Project last year from Europe and the United States. This is the next big science project. During World War II, it was the Manhattan Project, then the Connectome Project, and some people think the next big bandwagon could be the mind. And why are politicians interested in this? Because mental illness is one of the most ancient of all diseases. The Bible mentions mental illness. And one day, by mapping the brain, we may be able to understand mental illness. First of all, optogenetics. How do you combine these two fields together? It turns out that we can now put a gene inside a neuron, shine laser light on it, and the neuron fires on demand. This is incredible. There are videotapes now on the web where you have a mouse with lasers shining on the mouse brain. You turn on the light, and the mouse, you can command its physical movements. You could have it walk in circles. You could have it go to the left. You could have it go to the right, just by turning on a laser beam. So how does that work? Well, it works because of the photoelectric effect that Albert Einstein worked out in 1905. First of all, this is the opsin gene. It converts light into ion channel activity. So again, light into electricity, now at the molecular scale, and that's how your eyeball works. How does your eyeball work? Because it converts light into electricity, in this case, ion flows. Now that gene we've isolated. We can now put that gene into a virus. We make sure the virus is not dangerous, and the virus then infects brain cells at a very specific location. This means that we could take animals and actually find where the neural channels are for behavior. It's already been done on fruit flies. You can shine a light on the brain of a fruit fly and it will take off on demand. Push a button, it takes off. This has now been done on mice. As I mentioned, it's on the internet. You push a button, the mouse goes to the left, to the right, or actually runs in circles. Now, of course, some conspiracy theorists think that, this is a form of mind control. But for doctors and for people interested in the field, this also means insight into a whole range of mental diseases. Schizophrenia, depression, Alzheimer's, all these diseases, we're now beginning to understand the neural pathways, which was once thought to be impossible. We now are beginning to tease apart the neural pathways of these diseases. Also at Berkeley, where I got my PhD so many years ago, we can actually photograph your thoughts. In fact, we can actually photograph a dream. Here's how you do it. You take the brain, put it in an MRI machine. The machine is so good that it analyzes blood flow in 30,000 locations of the brain. So we now have blood flow on the left of 30,000 locations. Blood flow corresponds to oxygen being moved around, which corresponds to neural activity. Then you put these dots into a computer. The software program chugs and chugs and then prints out a picture. These are pictures of thoughts. We can now photograph thoughts using physics. On the upper left is the actor Steve Martin. Below that is it's kind of crude, but the fact that we can do it at all is amazing. Pictures extracted from the brain. You can clearly see that you're looking at people, not animals, or animals and not people. And then when you go to sleep and you dream, it begins to print out crude photographs of what you are dreaming about. This is amazing, something right out of science fiction. And one day when we have the Connectome project finished, perhaps by the end of the century, when we map the entire brain, what are we going to do with it? One possibility often mentioned is immortality. Because if you die, your connectome lives on forever. Your thoughts, your memories, your personality, your quirks live on forever as a software program. And so one day we could have a library of souls, whereby you go to the library and talk to your ancestors. I wouldn't mind talking to Albert Einstein, with all the memories encoded, with the ability to recreate a personality and things like this. I'm going to end on my application of this. I think in 100 years' time, we will not only have the connectome, but laser beams powerful enough to shoot that connectome into outer space. We'll put the connectome, your consciousness, your dreams, desires on a laser beam, shoot it to the moon. In 1 second, your consciousness will be on the moon. Sending it to Mars in 20 minutes, you'll be on Mars. No booster rockets, no weightlessness, no accidents, no radiation problem, no micrometeorites, no. 1 second, you're on the moon. On the moon, there is a computer which then downloads the laser beam, uploads it into a server, and then from the server you control a robot which is superhuman, a robot which can walk on the surface of the moon and explore the universe. I call this laser porting, and I think it is the most efficient way for an intelligent civilization to explore the galaxy. Forget listening in on a radio. Forget booster rockets. We're talking about riding on a light beam. In fact, this may already exist. I wouldn't be a bit surprised if aliens in outer space already have a network of laser beams by which their consciousness is zipping along at the speed of light, visiting distant worlds, inhabiting robotic bodies that can resist different kinds of poisonous atmospheres and things like this. Maybe it already exists. Maybe it's already out there. And then I'd like to end on one note and then invite 7 Nobel Prize winners up on the stage. I'd like to end on one note. When I was a child, I had a role model. Like many, it was Albert Einstein. And my favorite Einstein story is this. When Einstein was an old man, he was tired of giving the same talk over and over again. So one day his chauffeur came up to him, and the chauffeur said, "Professor, I'm really a part-time actor. I've heard your speech so many times, I've memorized it. So why don't we switch places? I will put on a mustache, I will put on a wig, I will be the great Einstein, and you can take a rest, put on my jacket, and be my chauffeur." Well, Einstein loved the joke, so they switched places. This went along famously until one day, a mathematician in the back asked a very difficult question. And Einstein thought, oh, the game is up. But then the chauffeur said, that question is so elementary that even my chauffeur here can answer it for you. Thank you very much. You've been a great audience. Thank you very much.
So, Michio, thank you so much for your vision of how our understanding of the world, the universe will change, our understanding of the brain and the universe come together. It's a wonderful vision for this. I think that we won't have to wait 100 years to see some of the things that we've actually heard about this morning in this fantastic vision. Michio, thank you so much.
Thank you.